So in this video, we're going to talk about Taylor polynomials and error bounds. So I think this is probably the section that's a little more cool about Taylor polynomials, and it kind of shows you how powerful these things are. So we've been saying has been that Taylor polynomials or a function itself can be expressed as a summation, okay? And we call this Taylor series. So n goes from 0 to infinity of the nth derivative of f evaluated at a, x minus a to the power of n divided by n factorial. So we were able to express some sort of function as a series. Now, sometimes a series will have a closed form, sometimes it won't. So, and one of the things that kind of depends on it is just basically this derivative to kind of see what exactly it's doing. So this is centered at a. So one of the really cool things about Taylor polynomials is the following thing. So we can estimate a function f of x near a by the nth partial sum of the Taylor series. Okay, at x, okay, and we call this the nth Taylor polynomial. Okay, so we're gonna call this the nth Taylor polynomial. Okay, and so basically what you're basically doing is that you're trying to estimate the function f of x with this Taylor polynomial, okay, t sub n of x. Okay, so I'm going to expand this series until the nth term, and then you're going to get some sort of estimation. So, for example, if I were to expand it right now, so if I were to expand this whole thing, you would see that the Taylor polynomial, or the nth Taylor polynomial, is going to be f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a whole quantity squared, and I can keep going all until I get to the nth derivative, okay, over n factorial x minus a to the power of n. So you can see here that what I'm doing is that I'm evaluating when n equals 0, adding it to n equals 1, then n equals 2, all the way until I get to the nth term, okay? So, for example, if I were to tell you what is the third Taylor polynomial, then what you will do, you will go up to all the way to the third polynomial, or the third or n plus 1th term, because we start at 0. So you'll start off with f of a, that's going to be n equals 0. Then you're going to do n equals 1, so f of a over 1 factorial x minus a plus f double prime of a 2 factorial x minus a squared, and then plus f to the third derivative of f over 3 factorial x minus a cubed. And one thing that kind of helps you figure out whether you've done this correctly is that in the end you should have a degree 3 polynomial, which you actually do, which is to the third power. So this is basically would be the third t sub 3. Okay, so if you're asking for the third polynomial, this is what you would have. Okay, so we're going to do a couple of examples, but let me go ahead and show you exactly what's going on so that you can kind of see. So what I have here, let me make this let me move this. So what I have here is basically the sine function. This is on Desmos. We have the sine function, and what we're going to be doing, so f of x equals sine of x, we're going to be changing the degree of n. So right now it's at a degree 0. Okay, so you can see that this purple line is n equals 0. And you can see that it doesn't even look like a really good approximation. So let me go ahead and increase this. So it'll increase different values of n. So then so if it goes to n equals 1, so let me stop it right there. You can see, you can see that near 0, okay, so this is going to be when a is equal to 0, you can see some sort of approximation, okay? So you can see that any value between maybe, it looks like around negative 0.5 to 5, this line will be a really good way to approximate the sine curve. And we've actually seen this many different times with linear approximations. So now if I wanted to do it with a degree 2 polynomial or degree 3 polynomial, this is what I'm going to get. So if you keep doing that, you can see that now this purple graph, the Taylor series, is making or tracing the sine curve a lot better. So if I keep doing that over and over again, so to maybe a 5th degree polynomial, you can see kind of like the tracing of the sine curve getting better and better as n increases. So see, it gets even better. So as n goes to 11, okay, so now we stopped at n equals 11, whoops, and n equals 11, you can kind of see that my estimation gets a lot better as the x values increase. So now I can kind of feel very confident in trying to figure out what x equals when x equals -4, and I'm going to plug it into the sine function. I kind of have a really good feeling about that that particular value to be very precise. So and actually this is basically what your calculator is doing. So your calculator isn't putting sine of 0.1. It's sometimes some calculators are using Taylor series, so because it's easier. So let me go back, because sometimes it's easier to work with a polynomial than it is to work with sine of 0.1. So this calculator doesn't do sine of 0.1. It kind of expands it to a polynomial, and then it plugs in the 0.1, which is what we're going to see in a little bit, which is actually really cool. Okay, nowadays the calculators can use some sort of interpolation method. So Taylor series is used in the calculators, but there's other different ways in which the calculator really does it. It doesn't just say, oh, sine 0.1, let me just look up this thing, and no, it has to do some sort of estimation. Okay, so so let's do a couple of examples so that we can kind of see, and then we'll talk a little bit about the error. So find the third degree Taylor polynomial of f of x is equal to e to the x at a equals 2. Okay. Okay, so we want to find the third degree Taylor polynomial. Well, lucky for us, we just wrote down the third degree Taylor polynomial right above here. Okay, so all we have to do is figure out or go to the derivative of the third power. So I got to take the derivative of e to the x all the way to the third power. Now, that shouldn't be too difficult, because if I were to have f of x is equal to e to the x, well, all of the derivatives are just going to be e to the x. So that should be really easy to do. So e to the x, and then f all the way to the third, e to the x. And now what I'm going to do is I'm going to plug in this value of a. So a in this case is equal to 2. So I'm going to plug in 2 here. E squared. And lucky for us, all of these guys are just going to be e squared. So they're not always going to happen like this, but you will get something that with exponentials is really nice. Okay, so now all we have to do is plug all of these things into my Taylor polynomial. So my Taylor polynomial is going to be T3 of x is equal to f of a, which is going to be equal to e squared plus the derivative e squared over 1 factorial x minus a, which equals to 2, plus e squared over 2 factorial x minus 2 to the power of 2, plus e squared over 3 factorial x minus 2 to the power of 3. So here is my polynomial. Okay, so instead of plugging in a number for e, we're just going to use this polynomial, which is a lot easier to work with sometimes. Okay, so now what we want to do, let's do this next problem using this. So maybe this was a part A. This is part A. Let's do this to be part B. We want to estimate using T3 of x. So using our third degree Taylor polynomial, we want to estimate this at x equals 2.3. Okay, so basically what you're going to do is just plug that thing in there. So you're going to plug in t sub 3 of 2.3, Okay, so we're going to go ahead and plug it in. So we're going to have e squared plus e squared over 1 factorial, 2.3 minus 2 plus e squared over 2 factorial, 2.3 minus 2 squared plus e squared over 3 factorial, 2.3 minus 2 cubed. Okay, so when you put this into your calculator, I end up getting 9.97153. Okay, so this Taylor polynomial gave me that thing. Now, if you were to compare the Taylor polynomial with the true value, so now our calculator, e to the power of 2.3, what we're going to do is if you put that in your calculator, you're going to get 9.974182. Okay, so this is what I end up getting. Okay, which they're kind of the same. So basically what you should kind of take away from this, instead of saying, oh, well, I don't understand, why do we have to do all of this work if I can just plug this into the calculator? Well, basically what your calculator is doing is not really putting e to the 2.3. What it's doing is just doing, it's taking an nth degree polynomial. So this whole thing, all of these terms, doing that and giving you this particular number. So all of this is just Taylor series. Okay, so there's not a magic function of e. Well, it works better with sine and cosine with the trig functions, but that's basically how this thing is being calculated using the Taylor series. Okay, all right, now that we looked at that, so what you can kind of do when you have this Taylor polynomial, you can find a polynomial to try to estimate the value and kind of see what the calculator is really doing. Something else that you can kind of look for is, okay, what if I were to try to estimate or use this Taylor polynomial to solve for my values? I know that if my degrees keep increasing, I'm going to get a better estimate. But if I decide to just use this third degree polynomial, how is my error going to be affected? Well, the way that your error is going to be affected is by something called the Taylor inequality. Okay, so what the Taylor inequality says is basically telling you how good, or asking you how good is your approximation. Okay, so that's basically what it's doing. Okay, so in order to find out how good your approximation is, this is the formula that we're going to be using. Now, don't worry so much about the derivation. The derivation is there, but I'm not going to derive it for you. You can look that up, but this is basically what it is. So this is what we call basically the remainder term. I also, in statistics, we kind of call it residual. It's just going to be the nth plus 1 derivative of f, take that in absolute value, divided by n plus 1 factorial x minus a to the n plus 1. Okay, so this is what we have. So the n plus 1. Okay, so what this does, it gives me an upper bound for the error. Okay, so it tells you, well, this error that I'm going to get is not going to exceed this particular number. Okay, which is actually really, really good. And this is for x minus a less than or equal to d. So x minus a less than or equal to d. Okay, so this is kind of like, you can think of kind of like the radius of convergence. Okay, so so let's go ahead and find that error. So find the error. Oops. Or find an upper bound for the error possible in using T3 of x for f of x equals e to the x at a equals 2 for x being between 1 and 3. So basically what this is saying is that if I use this Taylor polynomial that I just calculated, T3 of x, if I use this thing to estimate f of x equals e to the x at a is centered at 2, if I were to choose any values between 1 and 3, how is that going to affect my error? So what is the maximum error that I'm going to get? So one of the things that we're going to use is use this formula up here. Okay, so in order to do that, notice that we've used a third degree polynomial. Okay, so we use T3 right here. But we don't want T3. If we want to find R sub 3 of x, okay, for any value between 1 and 3, well, notice that we need to do a couple things. Well, n in this case is equal to 3, so I'm going to plug in 3 in all of these. So you're going to get less than or equal to absolute value of f 3 plus 1 of x. Oh, I forgot a parenthesis. Divided by 3 plus 1 factorial x minus a, which is equal to 2, 4 plus 1. Okay. All right. So now what I'm going to do, so this is going to be equal to f, the fourth derivative, divided by 4 factorial x minus 2 to the power of 4. This should be a 3. Okay. Okay, so now what we want to do is we want to find the fourth derivative. Now, luckily for us, the fourth derivative of just e to the x is just going to be e to the x. Okay, so that's just basically what that guy is going to be. And the whole point is that notice that there's a less than or equal to. We want to make this guy and this guy as big as possible. Okay, that's the whole point of this. So how can I make this as big? How can I make the fourth derivative, which is this guy right here, as big as possible? Well, if you look at all the values of x that I can take, e to the x is exponentially growing. So if I plot e to the x, it's just growing exponentially. So the bigger the x value, the more big this thing is going to be. So if I plug in 3, 3 will make this a maximum. So I'm going to have, so this guy is just going to be, let me plug that in, e to the x over 4 factorial x minus 2 to the fourth. So what I'm going to do is I'm going to plug in that 3 in there. E to the third over 4 factorial. I'm going to plug in the 3 in there too. 3 minus 2 to the fourth power. So what I'm going to have is e to the 3 over 4 factorial, because this thing is just going to be 1. And then the absolute value is just going to give me e to the 3. And this is going to give me 0.837. So what this tells me is that my error, okay, is not going to exceed this particular number, 0.837. Okay, so it'll be something that's less than 0.837. The absolute value is going to be something that's less between 0.837. Now I can overestimate or I can underestimate, but this error is not going to exceed this amount. Okay, so let's just do one last example. Okay. Okay, and actually let me do it in the next video because this video is getting long.